Okay, let's take a quick look at electron configuration. Now let's have an example. Let's say aluminium is number 13. If you're not sure about that, you look at the periodic table and sure enough, where is it? Here we go, aluminium number 13. Okay, so it's number 13, it has an atomic number of 13, it will have 13 protons. But we know that atoms are neutral overall, so all those 13 positive charges, they have to be cancelled out by 13 negative charges, so it will also happen to have 13 electrons, okay? So this atomic number up here says number of protons, but we know it's the same as the number of electrons. Okay, so electron arrangement 283. There we go. We put the electrons down, starting at the first shell, that got filled up, so we move to the next shell, that got filled up, etc. Okay, so there's the electron configuration of aluminium. Now that's, I guess, the junior version or the simplified version, but now we're going to the, wait, what's the actual version? Yep, more of a senior look, I guess. So we have electrons in shells. Now the maximum number of electrons in any shell is given by 2n squared. So in the first shell, we can have 2, and then we can have 8, and the third shell can take 18, next one 32, next one 50, etc., right? By calling n the shell number. N is actually the principal quantum number. In terms of atoms and their electrons, there are 4 quantum numbers. Well, shell number is the first one, the principal quantum number. Okay, so it just tells us how many electrons can fit into the shell. Bohr gave us this. The thing is, we're going not just to shells now, we're divvying the shells up into a subshell and then divvying up the subshells into orbitals. So what we have essentially is the shells. Within a shell we have a subshell, and then within the subshell we have orbitals. All right, so that's sort of the breakdown of it, I guess. Now, so the shells, first, second, third, fourth, etc., that's fine. In terms of what Bohr named them, the K, L, M, N, O, etc., right? But in terms of the subshells, well, the subshells have certain names. Their names are S, P, D, and F. All right, you'll notice it doesn't follow the alphabet. If we needed any more subshells, it would follow the alphabet. So it's actually S, P, D, F, G, H, I, J, K, L, M, N, O, etc. Right? The thing is, we don't actually need any other shells to cover all of the 118 elements. We only need S, P, D, and F. So there are our subshell labels. Now, why do we get these? Historical reasons. S for sharp. What have we got? F was fine, D is diffuse, and P, I can't remember something starting with a P, right? But SPDF, that's what we call the subshells. Now, within a subshell, we have orbitals. Now, an orbital will either be 1 electron or it will be 2 electrons. So we have orbitals within the subshells, but only with either 1 or 2 electrons. Now, these orbitals are actually quite funky shapes. Right? So here are the shapes of the orbitals. You can see the s orbital is nicely spherical, right? And the s orbital is nice spherical shape. The p orbital, it's not too bad. So that's s, has the p on this level. Now the p is not too bad. It's kind of dumbbell shaped, like it's kind of sticking out one side and sticking out the other side as well. But then of course it's in 3 dimensions. So we could have, that's the x p orbital. We've got the y p orbital. I'm not even going to bother trying to draw the z p orbital because I don't draw in 3D. And then of course we step it up a bit. The d orbitals and the f orbitals get really quite funky in shape, right? But thankfully this is not a video on shape of orbitals, so we're okay. So within a shell, we know about shells, first, second, third. Within the shells we have subshells, we call them S, P, D, and F, and within every subshell we can have an orbital which can have either 1 or 2 electrons. Now, the different subshells can have a different number of orbitals. So let's just draw up a little table. Let's call it subshell. Lovely. Number of orbitals, because the different subshells do have different number of orbitals. And then we have the maximum number of electrons. Right? The maximum number of electrons. In fact, I should probably say maximum. A line with a little line through it, that says maximum, right? So this line with 2 dots would say minimum, right? Grand, just a little shorthand there for you. So the maximum number of electrons. Cool, so here's our table, let's populate it. Well, we know the hey, go away, there we go. We know the subshells are S, P, D, and F. Grand. Now, the S subshell can have a maximum number of 1 orbital. And of course, an orbital could be 1 or 2 electrons, right? So the maximum number of electrons in that S subshell is going to be 2, okay? Because it's only had 1 orbital, which can take a maximum of 2 electrons. Cool. So a P subshell can actually have 3 orbitals, and of course every orbital could have maximum of 2 electrons, so that's going to give us another possible 6 electrons in that subshell. And then we just go up with the odd numbers, and then we go up by the even numbers, but we go up by 4s. There we go. So here's our table here. In a D subshell, we could have a possible of 5 orbitals, and that means we can have 10 electrons, right, in the D subshell, because 5 orbitals, but every orbital can have up to 2 electrons, okay? So, cool. You don't have to memorize that table. Really, here's the part that you do need to know. You do need to know that S goes up to 2, P goes up to 6, D goes up to 10. Oh, that's not a D, that's a 10. Hang on. D, there we go, goes up to 10, and F goes up to 14. This is the part to know, right? You don't have to memorize that table, waste of time, but do know this, that you can have 2 S electrons, S subshell electrons, you can have 6 P subshell electrons, 10 D subshell electrons, and 14 F subshell electrons. Great. Now, how do we put all this into play to write the electron configuration? Well, there's another thing you need to be introduced to, and that's this. This is your roadmap, essentially, for writing the electron configuration of any element. Okay, so basically, just follow the arrow, and it tells you what to do. Right? So follow the arrow, we go down here. Oh, I just passed through the 1s. Okay, so we're going to start with 1s. And then then I have to sort of loop back up, and then I come down through the 2s. Okay, well the next one is going to be the 2s. And then we're off the chart, so we loop back up around, and then we hit the 2p followed by the 3s. Okay, we've got 2p, 3s. And then what? Well, then we've got the 3p and then the 4s. So then we've got the well, let's just sort of, I guess I'll write it on the next line. Then we have the, what did I say, 3p, 4s. Now, what's after that 4s? Let's loop back up, and we're coming down this way now. We've got a 3d. Now, hang on. This is where something may make sense, something from earlier. Remember those 19th and 20th atoms, potassium and calcium, when we were writing the electron configuration? 2, 8. Now the next shell can take 18, but we don't. We only put 8 there, and then we actually start the 4th shell. And calcium similar to 8, 8, 2, right? Why did we start the 4th shell? That 3rd shell was not full, right? We know this 3rd shell, that can actually go up to 18. It's not full at 8, but we did start the 4th shell. Well, yeah, because essentially we were following this roadmap even without having met this roadmap. Because look, we start the 4th shell, and then we come back and do more in the 3rd shell, right? Now, if you remember your numbers, okay, in the D, we can have 10 electrons, which is why, let me just find where I was, there I was, which is why when we come back from elements 21 to 30, we come back and we fill up that 3rd shell up to 18, because we're now doing the 3D subshell, and of course that can take another 10 electrons, okay? And the S can only take 2 electrons, which is why we only put the 19th and the 20th. We started that 4th shell with 2 electrons. That was corresponding to the 4s1 and then the 4s2, and then we come back and fill up the 3rd shell with its D subshell, which is another 10 electrons. So, like I say, at number 21, we'd come back and we'd call that 8 and 9. Number 22, we'd call that a 10. And we would eventually fill up that 3rd shell up to the 18 that it could take, because now we're in the realm of this 3D, and it goes up to 10, right? Okay, so aluminium. Let's look at aluminium. I think that's what we started with. Yeah, it was. There we go. We'll do it on this this slide right here. So aluminium, that's the electron configuration of aluminium. Yep, grand, that's the, let's call it the junior version or the simple version. Now we'll do the actual version by following the roadmap. We start at 1s. Okay, so here's our roadmap. Let's just tidy that up somewhat. There we go. This is the Aufbau roadmap, by the way, the Aufbau electron configuration we're doing here. Let's scroll that down. Aufbau, we're talking now. Aufbau electron configuration using the Aufbau roadmap. So, like, it gives the same information, but it actually gives more information. We'll have a look at that after we do aluminium. So, we've got our 1s. Great. How many electrons could the S subshell take? Well, remember, it can take 2. Remember, I said those numbers to just know these ones. S can take 2, P can take 6, D can take 10, F can take 14. Okay, so we're on an S, it can take 2. Lovely, it's full. It can only take 1 or 2. I've put 2 there, we need to go to the next one. So our next one, loop it back around, 2S. So, okay, let's write down our 2s. Now, of course, that can take another 2. And then if we look at our roadmap, then we're, go away you. Then we're at the P, the 2P, and then the 3s. Okay, so we're at the 2P. Now, that could take 6 electrons, so let's 2p6. All right, now how many have we actually used now? Okay, we just need to keep track of how many electrons have we used as we go along. Well, I've used 2 here, 2 electrons here, another 6 there. I've only used 10. Okay, so I've still got another 3 to do, so I start my next part and I follow the roadmap, and after 2p was 3s. All right, now that can take another 2, but I still have 1 more, so we go back to our roadmap. And what's after the 3s is the 3p. So I go back here and I start my 3p. Right? Now, we know that can take 6, but I don't have that many. I've only got 1 more. So, okay, done. That is now the electron configuration, the Aufbau electron configuration for aluminium. And I just got rid of the 2, put that back. There we go. So the version at the top, this is the electron configuration of aluminium. Lovely. And we might use that sometimes if we're trying to work out what ion the aluminium ion is. But really, in terms of electron configuration, the better version is down below. It still, as I mentioned, gives us the same info, right? Here, I've got 2 electrons in the first shell. Well, okay, first shell, I've got 2 electrons. No problem, it tells me that. Here, 8 electrons in the second shell. Well, in the second shell, I've got 2 electrons. But look a bit further, also in the second shell, I have another 6 electrons. Well, those 2 together, there are my 8 electrons from the simplified version, right? In the third shell, I have 3 electrons. Yep, okay, well, in the third shell, I have 2 electrons. But also in the third shell, I have another electron. Well, that gives me my 3 from the simplified version, right? So it does actually give us the same information. The thing is, it actually gives us more information. So it gives us the same plus a little bit extra, which is why we like it, right? It tells us not just how many electrons into shells, but what orbitals they are in. Are they in an s orbital with a certain shape, or a p orbital with a different shape, or a d or an f with different shapes again? Right, so this is how we now write the electron configuration. Let's do another example. Let's look at, let's go back to our periodic table here. Why don't we do neon? Let's do neon, just because we can. Now, because I want to point something out, we're going to, I was going to say do it on the same slide as aluminium, but let's not. Okay, well, let's do it this way. Let's do neon here, and let's do aluminium here. Now, we've already done the aluminium. We just need to, I guess, redo it. We had 2, no, we don't. What am I talking about? We start at 1, first shell, there we go. 1s2, 2s2, 2p6, 3s2, 3p, and then we had a 1. Okay, so that's our electron configuration for aluminium. Now, neon, let's have a look. It's numbered 10 on the table, so we're going to use 10 electrons, and we'll be doing a 1s2, 2s2, 2p6, and I've actually used my 10 electrons, so that's it. Neon is finished, okay, just following the roadmap. Now, look at these 2 carefully. And what do you notice? Well, hopefully you'll notice that a lot of aluminium's electron configuration is the same as neon. Okay, now you can see aluminium is longer, right? Neon is number 10, aluminium is number 13, it's longer. But it's only number 13 and already it's starting to get a decent bit of length to it there. Imagine if someone asked you to write the electron configuration of gold. You'd be writing right across the page, right? We've got a nice little trick so that we can shorten it. What we do is we pull out the previous noble gas. Okay, and I chose neon because it is actually the previous noble gas. Okay, so this long version for aluminium is absolutely correct, but what we can do is also write the electron configuration for aluminium. We can say, well, you know what? It's the same as neon, so square brackets around the symbol for neon, and then it's got a little bit extra, and we only need to write now this little bit extra, 3s2, 3p1. Okay, so there's a bit of a shorthand there, right? So you could write the whole thing out, and you might be asked to write the whole thing out, but if you're not specifically told, write it all, then you can use this little shortcut. In fact, you may be asked to write it out in full and the shortcut just to show that you know what you're doing, right? But the shortcut is we pull out the previous noble gas, and in this case, that was neon, which takes us up to here. So this is the electron configuration of neon, so pull that out and say, oh, look, it's just like neon, plus this extra bit. Okay, so that's how we do the electron configuration. But wait, we're not done. There's a little bit more to it. We actually have an exception to the Aufbau configuration. So let's go back to our roadmap. Now hopefully this started to make more sense why the 19th and 20th electrons, you actually start the fourth shell and then you would come back because we're starting our 4s, but then follow the arrow, we come back and we fill up that third shell with another 10. Remember the D subshell can take another 10 electrons because 5 orbitals, 2 each. So that's actually not a little exception anymore. That's hopefully explained, but there is an actual exception. Now the exception to the rule, there tends to always be one, is that a D, let's say a D with 5 electrons, right, D subshell with 5, or a D subshell with 10 electrons, either of these two options are more stable. Now remember, atoms are trying to get stable, right? They react to get stable. So either of these two configurations, D5 or D10, are actually more stable than the S of the next shell. Right? So if a D subshell is half full because it's got 5, or if it's full because it's got 10, that makes it more stable than a full S of the next shell. What the heck does that mean? Well, let's go and do an example. Now, the example we're going to choose is number 24, chromium. Right? So we'll look at chromium. So first we'll just write the electron configuration of chromium. So chromium Cr, it's number 24, 24 protons. It will also have 24 electrons. Grand. Let's throw them down. Following the Aufbau roadmap, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, because the 4s, remember that was the 19th and 20th, okay, that's for potassium and calcium. But then we come back and we start filling up that third shell up to what it should be. So we now go 3d, right? And we'll have another 4 here. There we go. So that is the electron configuration of chromium, except it isn't, right? Because remember, a D5, right, or a D10 is more stable than a full S subshell from the next shell. Well, this is very nearly D5, so nearly there. And if it were D5, that would actually make it more stable than this, the next shell, S. Okay, so what actually happens is an electron gets stolen from here. That's not a 2, that's now a 1. And it gets given to here, so that's not a 4, that's now a 5. So that's the actual electron configuration of chromium. Let's just write that a bit more cleanly. Okay, so we have to do the 4s, so 4s1, then 4s2, and then 3d4. But we steal one from the next shell's s, so we've stolen one and given it to the d to make it d5, because that makes the atom more stable, because it now has a d5. And that makes it more stable than the next shell. So here it was the 3d5, so the next shell we need to look for the 4. Here we go, so the 4s. Right, makes it more stable than a full 4s, so we can steal that electron there. So there we go. Now, what if we were doing the next one, number 25? What is number 25? I can't think off the top of my head. Bring up the table. We have manganese. Okay, so manganese. Go back, there we go. Manganese, number 25. Well, what's its electron configuration? 1s2, 2s2, 2p6. 3s2, 3p6, 4s3d. Now, manganese, number 25, it's going to finish with a d5. We've already got a d5, right, up above from our chromium. But remember how we stole that electron from the 4s, from the s subshell of the next shell, to put into the d, making it d5, yeah? Well, we've already got that d5, but now we can... we've got one more electron, we can put it back into that 4s2. So we will eventually go back and top that up. We stole one, we feel bad, next element, we'll put it back. Everyone's happy. Okay, cool. Now, what was the shortcut though? Let's do a shortcut. Remember, we can pull out the previous noble gas. We don't necessarily need to write everything. So we find our chromium. Periodic table, there it is. We pull out the previous noble gas, right? So the noble gases down here, down group 18 are the noble gases, and the previous noble gas was argon. So we can pull out argon and say, well, the electron arrangement of chromium is essentially the same as argon. So we can write it as essentially the same as argon plus that extra little bit, okay? So argon took us to number 18, so we've got 2, 4, we got 10 here, there's another 2, there we go, so up to there, that's as far as argon goes. So we can say that the electron arrangement of chromium is the same as argon plus 4s1, 3d5. Okay, so remember we have that shortcut method, just makes things not quite as long. Because look, this long, and we're only at number 24. Like I say, imagine if you had to write gold, right? So there we go. There is electron configuration and the exception to the Aufbau rule. Right? So remember, a D5 or a D10, if we can make it those, do so, because that would be more stable than a full S subshell of the next shell. So you sort of steal one from the next shell's S. Okay? All good? Grand. Done. Now, before we wrap this video up, I do actually want to show you one more little trick which can make life easier. Let's label some more of this periodic table. You can see that they've already been labeled all sorts of stuff. Well, group 1 and 2. These guys, oh, that was a terrible circle. Circle-ish, ovalish, there we go. These guys are known as the S block elements. Okay, remember, SPDF, okay? From group 13 through to 18, these are collectively called the P block elements. The transition elements, here we go, from group 3 to 12, these are the D block elements, and the lanthanoids and actinoids are known as the F block elements. Now, this will actually help you because, you know, it's one thing to write out a long electron configuration, but you have to keep in mind to keep track of all the electrons as you go, you know. So we start writing out for chromium. In fact, let's just go away. There we go. Let's do chromium. Okay, so it's 1, S2, 2, S2, just following that roadmap, remember? 2, P6, 3, S2. Now, oh, hang on. I must keep track of how many electrons I'm using, right, as I go along, because I need to use 24. What have I used? Okay, so I've used 2, 4, and 6. Okay, I have 10, 12. Okay, so I've used 12. I can keep going, right? So then we can go 3p6. All right, so now I've used 18, and then I can go 4s2. I've used 20, and then I can go 3d. So we can do that fine, but you have to keep adding these things up so that you don't go too far, right? It would be good if there was a way to remember where to stop. Well, there is, and I just showed it to you. So here we go. By knowing that we have these S block elements, the P block, the D block, and the F block, we find the element that you're talking about. So we were doing, what we were doing? We were doing chromium, right? Number 24. And that will tell us where to stop. Okay, we're going to stop at a D, because it's a D block element. Okay, now it's the fourth D block element along, right? So we've got, it's the 1, 2, 3, it's the fourth one along the row of the D block. So we're going to finish with D4. Okay, now remember, it wanted to be a D4, but then we remembered that Aufbau exception, so we actually stole one from the next shell's S and put it in to make it the D5, right? But just by itself, at first glance, it was the D4, right? So that's telling us where to stop. Now, what number D4? Like, is it 2D4, 3D4, 4D4? Where is it? Well, we look at the period, the row that the element is on. Now, unfortunately, the D block, we just have to sort of imagine it was lifted up by 1, right? So that first row of the D block elements, it's actually in the fourth period of the periodic table, okay, the fourth row. Remember, a vertical column is a group and a horizontal row is a period. What we need to do to get the finishing point of where to stop is just pretend that D block was lifted up by 1. So instead of 4, because it's fourth row, so instead of finishing at 4D4, oh wait, it's a D block, we have to sort of lift it up 1, so we get rid of that 4 and call it 3D4, right? So there's our finishing point for chromium. And sure enough, that was our finishing point, but then we just remembered, oh wait, also Aufbau exception, it's going to steal 1, so it becomes a 3D5, right? So let's do 2 more examples. Let's find the electron arrangement, and let's just tidy this up a bit. Let's find the electron arrangement of selenium. Right, can you spot selenium? The periodic table is there. Did you spot it? Did you spot it? Hopefully you were looking about here. There's selenium. Number 34. Now that is a P block element. Okay, remember, in fact, maybe I should have left the labels. We have S block, the transition elements, the D block, 13 to 18, the P block, and the lanthanoids and actinoids are the F block. So selenium is a P block element. We're going to finish with a P. Now count them along. It is the 1, 2, 3, 4th P along, right? It's the fourth one along of the P. So it's going to finish with P4. Okay, now which row is it in? Which row of the periodic table? Well, here's the first row, second, 3, number 4. So it's in the fourth period. It's going to finish with 4, P4. Okay, so that's where we finish. So now, in order to write the electron arrangement of selenium, and remember it was number 34. Was it 34 off the top of my head? Yes, 34, grand. But it's going to finish with a 4p4, right? So now we just throw down the Aufbau roadmap and fill it in as we go, right? So we've got 1s, 2s, 2p, except just following that roadmap, but fill it in. Well, s can go up to 2, s can go up to 2, p can go up to 6. Okay, so what have we got next? We must have a 3s2, 3p6, 4s2, 3d10, 4p. Oh wait, 4p, that rings a bell. 4p is going to be our finishing. So 4p4. There we go. And now, without needing to actually count the electrons, we've used the right number. Okay, we can do a check on that, because here we have 2, 4, and 6 makes 10, and here's another 8, so we're at 18, there's 20, there's 30, 34. Sure enough, we used our 34 electrons. Okay, so We could have done it just by counting those electrons and keeping track of them in our head until we'd used 34. Or, in my mind, a much simpler way to know when to stop is to just look at which block it is in, how many of that block it is along, and then which period it's in. But remember, the D block, we sort of have to pretend that it's fallen down, so we just got to lift it back up, right? So if we were doing, if we were doing gold, right, that long one I keep mentioning, it's number 79. Oh my goodness, how am I going to keep track of all those 79 electrons? Well, doable, right? We're just adding up as we go until we get to 79. Or we can say to ourselves, I'm just going to follow that Aufbau roadmap. I'm not going to think about the numbers of electrons at all, but I am going to stop at, let's see, the first row of the D block we're calling 3, so this is 4, so this is 5. So for gold, we'll stop at 5. It's a D block, and it's the 9th one along, so it'll stop at 5D9. And then when we do it, then we're going to remember, oh wait, that Aufbau exception, so we're going to steal one from the 6S2, so that'll be 6S1, and then we'll make it 5D10, right, because that'll make it more stable. Okay, so that's how we would know when to stop for gold. Yeah, so let's just do one more example, just because we can. Let's do, I don't know, what should we do? Let's do barium. Let's write the electron arrangement for barium. So barium is number 56, right? So barium is number 56, 56 protons, therefore 56 electrons. Let's put them all down. But wait, where should I stop? Well, if we look at barium on the periodic table, it's an S block. So we're going as far, we're going to go as far as S. Right, it is in the, what have we got, the 6th period, the 6th row, so we're going to go as far as 6S. And it is the 2nd along, so it's not going to be S1, it's the 2nd, so it's going to be S2. So here's my stopping point, right? Barium's electron configuration will stop at 6S2. So now I just need to follow that Aufbau roadmap, this one here, and I'm going all the way down to this 6S. All right, so let's do that. Let's write the electron arrangement for barium. Well, following that roadmap, what do we have? 1s2, 2s2, 2 p6, 3 s2, 3 p6, 4 s2, 3 d10. Then we must be back at the 4 p6. And after that, we've probably got a 5s. Let me just check. Where did I get up to? I got up to 4p. So, yep, 5s. And then we're back to the 4d. Okay, so we just follow that roadmap. Yeah. So 5s2, 4d10. Then we'll be at the 5p6, followed by the 6s2. And let me just check that after the what we got up to? We got up to the 4D, 5P, 6S. There we go. So we just follow that roadmap. And, oh, wait, that's where I stop. Done. So that is the electron configuration of barium. And if we were to add up all of those numbers, we'd find that sure enough, by all those numbers, I mean the numbers of electrons, right? Well, here's 10. And here's another 10. There's another 10. So we're at 30. There's 40, 46, 48, 50, 56. Yep, absolutely. That's the right number of electrons. That really was the place to stop, right? 6s2, because it's the 6th row of the periodic table, right? The 6th period, and it's an S block, and it's the 2nd element along that S block. So it finishes with 6s2. So that's a good way to know, when to stop. And then, of course, for barium, instead of writing all that out, of course, we have that shortcut. We find the previous noble gas. That would be xenon. And so to save us some time and space, we just say, well, actually, barium's electron configuration is the same as xenon, but it's got a little bit extra, right? Now, xenon is, all of the noble gases, in fact, finish with the P6, right? So xenon takes us as far as here. That's my last P6. So it's the same as xenon, plus it's got a 6s2. And you'll see that is actually much shorter, right? Much quicker and shorter to write this than the whole thing, right? But like I say, you might be asked to write the whole thing. So anyway, you know how to do the whole thing now, and the shortcut, and the exception to the Aufbau rule, and you've got the roadmap, and oh, where do I stop? Well, we've looked at where to stop. So there we go. Electron configuration, grand, done.
Don't forget to hit the like button. Yeah. And subscribe to It's Up Here. And here's another video.